All right, in this video, I'm going to look at solving absolute value inequalities. So, kind of a kind of simple example would be something like the absolute value of x is greater than a. So what does that even mean? If we kind of remind ourselves, absolute value of x is the distance x is from 0, then what is this really saying? Well, this is saying that, if I look at the number line here, I got 0. And the absolute value of my number, the distance my number is from 0, is a units away. So, somewhere over here, there's the number a, whatever that number is. And my number that I'm taking the absolute value of is farther than that away. It's somewhere over here, in this area. But it's not a. A doesn't work here. And I'll show an example where a would be included in this set, but a is not included in the set. We're somewhere over there. But that's not the only way we could be a units away. We could also be over here at negative a. And that would also be a units away. So I want to be more than a units away, which means I could be, somewhere over in this area, somewhere going, farther than a units away. And if I say, well, let me kind of describe what I've shaded here, and I'll use set builder notation to describe that. So x such that x is less than negative a away, or x is greater than positive a away. Same number can't be in both, or in this case means we're combining elements from each set, that as long as a number satisfies one of these two statements. Could that satisfy both? You could have a situation where things overlap a little bit or something, but as long as it satisfies at least one of them, then it's in our group. So, if you're picking a number less than negative a, that will satisfy this part, so that's in our group. If you pick a number bigger than positive a, that would be satisfy the second part of the statement, and that's in that group. Another way you could write that is in interval notation, looking at that graph. And interval notation uses bookends to kind of describe this set. So, this shaded part over here, how left it goes, theoretically, it approaches negative infinity. Now, it'll never actually get there, so this will always be a parenthesis on one of these affinities. Whether the other end's a parenthesis or not depends on, this inequality symbol. But one part of our answer is it goes from negative infinity all the way up to whatever negative a is, but not quite there. So we're going to put a parenthesis there. And then we'll union, that's the same thing as or. Using interval notation, use the union symbol, and then we're going to pick up right past a. So again, that's a parenthesis, and then it goes all the way up to the right, and so we're going to put a parenthesis again because you can't get to positive infinity. So those are two ways of writing that answer. But if we look at this, absolute value of a, what this is saying is your number is more than a spaces away from 0. That's what that statement's saying. More than a space. So when you're more than a spaces away, that means you're farther to the right or farther to the left than a spaces. Now let's compare that with the absolute value of x is less than b spaces away. So again, I'm looking at this number line. I got 0, and my number, its distance from 0 is less than b spaces away, b units away. So, again, I have a number b over here, space b. Well, I'm actually closer than that here to 0. So I'm in this area, and again, it's not equal to b. In fact, I could be right on top of 0. That is a possibility there. So it's everywhere there. But, once I get past 0, then I have to be worried about, I might go too far. And so, well, how far left can I go? And the answer is, well, there's negative b over here. That's b spaces away. So you can't go that far. So you have to stop right before you get there. So And I can go that far, and then I got to stop before I actually get to negative b. I can get as close as I want to it, but not actually to it. Now, if I write this in set builder notation, this is x such that, so I want my numbers between negative b and positive b. So the way I write that in set builder notation, I would say negative b is smaller than my number, but at the same time my number is smaller than positive b. In interval notation, I would say, oh, I could pick up right past negative b as long as I stop right before positive b. And again, those both are included. Now, I want to kind of connect these two together. This statement is actually a double statement. And so this statement means the following. This is saying x is bigger than negative b, and at the same time, x is less than positive b. This single statement is saying both of these statements. Now, the reason I want to point that out is when we talked about absolute value equations, we solved two problems whenever you dealt with an absolute value equation. Now that we're looking at absolute value inequalities, when I look at this or, this first one, notice I got two statements, or this or that, this or that. And then on this one, I got two statements, this and this. So I'm still getting two statements. It's just in this case, this and case, I merge those two statements into a single statement, a single double statement. And that's what you're going to want to do. But initially, you might want to think about it this way. Now, I want to point out something here. Let's see if I can get up here. I think he is not letting me go up there. I don't know why. What's going on here? All right. Let's click on that. Okay, so notice here I have x greater than a. Well, notice here I have x greater than a. The same thing. And over here I had, the second one I had x is less than b. When I split this into two problems, notice I got an x is less than b. Then, if I look at this, x is, notice the second one, I still had the x, but this time it came out to be less than negative a. So notice how the inequality was a greater than, now it's a less than. The value outside was an a, and now it's a negative a. Same thing here. This was x less than b, and now I have the second one that x is greater than negative b. So just like when I was solving equations with absolute values, I got two problems, and I changed the sign of the outside part. I'm going to do that here, but I'm also going to change the inequality symbol as well. The key here is, though, I need to know whether it's an and or an or. That's the real secret to doing these types of problems. So let's say I have, well, just real quick, I'm going to say, if you have the absolute value less than or equal to c, then you're going to say x is less than or equal to c, and x is greater than or equal to negative c. This less than is telling me I need an and. Now, if I had the absolute value of x was greater than or equal to c, then this would be x is greater than or equal to c, or x is less than or equal to negative c. So if you start with a greater than, then that's going to tell you you're going to need an or. Now, notice this absolute value is by itself. So if that's not the case, you got to move things around till you get it this way. But this is going to be, or this is our key here. And less than is going to tell us and. Greater than is going to tell us or. And that goes back to what are we talking about? We're talking about distance you are from 0. So if you're less than a certain distance, you're kind of combined in that middle area, close up to 0. Whereas if you're talking about a distance greater than something, you're off to the two pieces. So you're not going to have those two pieces together, usually. So let's look at solving some problems here. So say I want to solve, whoops, I want to solve absolute value of 4x minus 3 is greater than or equal to 7, say. Okay, so first thing I'm going to notice, and this whole or and thing only deals with absolute values. If you had a problem without absolute values, you would not have an and or an or. You just do the problem directly. But this, because we have an absolute value, we're going to get two problems, and we need to decide, is the relationship here an or an and? So as soon as I see this absolute value is greater than, that's an or situation. And I'm going to get one problem that's going to look pretty much the same as what I started with here. And then I'm going to get a second problem where I'm going to take 4x minus 3, this inside part, not change it. Instead, I'm going to change this outside part. This is going to become now a less than or equal to negative 7. And I should get two pieces here, two separate pieces usually. So 4x is greater than 10, divide by 4. So x is greater than or equal to 5 halves. Add 3. 4x is less than or equal to negative 4. Divide by 4. So, or x is less than or equal to negative 1. And there's my solution. If I want to graph this, then remember you put things in numeric order, not necessarily how you wrote it down. So negative 1, positive 5 halves. X is less than negative 1, less than or equal to. So because it could be equal to, I'm going to use a bracket. Less than or equal to, it's going to go that way. So yeah, like I said, I'm farther away in two different directions. And then x can be greater than or equal to negative 5 or positive 5 halves. So go this way, and there's my graph. And if you want to do interval notation, then you could do negative infinity to negative 1, including negative 1. You use a bracket, parenthesis, 5 halves, bracket again on 5 halves, up to infinity, parentheses. Notice that infinities are always parentheses because you can't ever get to infinity. But 5 halves and negative 1 do work for solutions to this type of problem. Let's say we instead had, let's solve 4 minus 3, absolute value of x plus 6 is greater than negative 8. You say greater than, that means or. No, we can't make that determination yet. First, we need to get this absolute value thing by itself. Then we can decide if it's an and or an or. So what I want to start off by is getting rid of this 4 and get rid of this negative 3. So I'm going to subtract 4 from both sides. Negative 3, again, that sign goes with the 3. X plus 6 greater than negative 12. Now I need to get rid of this negative 3. Divide both sides by negative 3. Absolute value of x plus 6. Because I divided by a negative from your knowledge of solving just standard regular inequality statements, you know that if you divide or multiply by a negative, that's going to change that sign to a from a greater than to a less than, and then negative 12, negative 3, positive 4. Now I can set up my two problems, and I know that now that this is a less than, that's an and. So it's going to be x plus 6 is less than 4. So again, I'm going to get one that looks pretty much exactly the same, except with no absolute values. And then I'm going to get a second one, x plus 6 is greater than, so I'm going to change the inequality symbol, negative 4. And I'm going to solve each of these. So I'm going to subtract 6. X could be less than negative 2, and subtract 6. X has to be greater than negative 10. What does that mean? If you want a number smaller than negative 2 and at the same time bigger than negative 10, that means you want a number between negative 2 and negative 10. And notice this relationship hasn't changed. X is less than negative 2. X is less than negative 2. X is greater than negative 10. Well, negative 10 is less than x. That's the same as saying x is greater than negative 10. So it's the exact same relationship, but where we had two problems, we merged them together. So anytime you have an and, you're going to have to try to merge those into a single statement. And again, if you want to draw that on the number line, -10, -2. Remember, zeros over here. Usually I wouldn't graph 0, but just kind of remind you that zeros over here. So 2 back and then your 10 back. That's why it's graphed that way. And neither end is included, so kind of graph that like that with parentheses. And if you want to do interval notation, -10 to -2. And some of the problems may ask you to do a specific notation, so that's why I'm showing you both. If it didn't ask you to do it, just says solve it or solve it and graph it, then I could have stopped with these first two things and not have done the interval notation. But sometimes you might need to do both. All right. So let me real quick kind of jump back here. So once you have an absolute value by itself, if you have a less than, whether it's greater than, whether it's less than or equal to, or just straight less than, that's going to be an and situation. And if you have an absolute value greater than or equal to, that's going to be an or situation. Now, kind of the way that can help you remember that, kind of a little mnemonic device, is you can look at this less than and look at it kind of like a crooked L. And this would spell and land. So you put those two together, land, and that maybe that'll help you remember those two. And then this is not an L, so it doesn't go with and. So if you just remember land, then the not L must go with or. It's and or. Those are your two choices. Look at it that way. Okay, so let's look at some special cases here. Let's say we have the absolute value of x minus 4 is greater than -3. And let's say we have the value of x minus 4 is less than -3. Now, without doing any work, I know the answer to both of these. And hopefully by the end of the semester, you will be able to do that as well. Hopefully by the end of this section, you'll be able to do that. This answer here is all real numbers. Or if you want to write interval notation, you'd say it goes from -infinity all the way to +infinity. All real numbers. Set builder, you could say x such that x is an element of the real numbers. That's kind of a symbolic way you could say all real numbers. This one is no solution. So how does that work? Let me prove those are the situations, and then I'll explain why I can do it without proving it. So let's say I want to solve the absolute value of x minus 4. Ew, that's not nasty looking absolute value. Let's get rid of that. All right, let's try that again. Absolute value of x is greater than -3. So again, this is not an L, not an and, so it must be or. X minus 4 is greater than -3, or x minus 4 is less than +3. And so if I'm going to solve these, add 4, x is greater than 1, or add 4, x is less than 7. So let's look about what that looks like on the number line. This is saying that if I have 1, and I pick any number greater than that, that's going to satisfy this part of the problem. And if I have 7 and I pick any number less than that, it's going to satisfy this part of the problem. Now you might think, well, shouldn't the answer be between 1 and 7 where they overlap? But that's not what or means. Or just means it has to satisfy one of them. It has to satisfy at least one of them. It could satisfy both. So from numbers from 1 to 7, not including 1 and 7, satisfy both statements. But that's not or doesn't require it to satisfy both statements. Or just requires it to satisfy one statement. So any number along this path going to the right satisfies the first statement. And any starting at 7 going to the left, any number over there satisfies that statement. Because these overlap, that means it's every number satisfies at least one of these two statements. And that's what or requires, is at least one of them is satisfied. Doesn't mean both have to be satisfied. Only one of them has to be satisfied. So the fact that these overlap in this way, and it's an or, means this is all real numbers. Now, let's say I look at that second example, special case. Solve what happens when I have the absolute value of -4 is less than -3. Well, again, this looks kind of like an L, And I say, well, that tells me land, right? That's the and situation, kind of land. That's a little mnemonic device you can think of. So x minus 4 is less than negative 3. X minus 4 is greater than positive 3. Again, change the inequality, change the symbol. So I'm going to solve these, add 4. So x has to be less than 1, and add 4, add 4. X has to be greater than 7. Now, let me look at this graph. What does this look like? So 1 less than, x is less than, so I'm going this way. And x is, so I got 7, x is bigger than 7, so I'm going greater than 7, I'm going that way. Now what and means is, what do they have in common? What are the numbers that satisfy both of these statements? Or in other words, where do these overlap at? So give me a number smaller than 1, and at the very same time, that same number is bigger than 7. And you can just see this graph doesn't overlap at all. This is no solution. You could also use this symbol. That means the empty set, or you can use that. That also means the empty set. But you just say no solution if you want. So there's no overlap here, because with an and situation, all the conditions have to be satisfied. It has to, the number has to be smaller than 1, and at the same time it has to be bigger than 7. That's impossible. This doesn't work. So if there is no overlap in an and situation, there can't be any answers to that. Now, that's how you could prove it. That's how you could work it out and show that those are not. Now, how did I know without doing all that? Well, I made up the problems. That's one of the reasons I knew. But, how did I know that they needed to be made up that way? Well, remember, the numbers you get from an absolute value, the smallest they can be is 0. No matter what number you plug in here for x, when I take the absolute value here, the smallest I'm ever going to get is 0. That's if I put a 4 in there. If I put any other number in there, I'm going to get something bigger than 0. So, if I put like negative 20, this would be negative 20 and negative 4 make negative 24. Absolute value is positive 24. So anything I calculate in here is always going to be bigger than a negative, no matter what that negative is, because it's always going to be at least 0 or bigger. So any number is going to satisfy this. On the other hand, the same thing. I'm never going to get a number smaller than negative 3. In order to be smaller than negative 3, less than negative 3, you would have to be, a negative. And this will never calculate out to be a negative. The least it will ever be is 0. So since this can never calculate out to be, with the absolute values, ever calculate out to be a negative, there's no way I can get an answer that's smaller than negative 3. So that's how I knew, without doing all those work. The work verifies it. And if there was a problem like this on a test or something, you might say, well, I think it's this, but I'm going to go ahead and try to show some work, just to cover my bases here. This would be another way to do it. All right, let me kind of give an alternative approach here. And I'm going to do both. I didn't do it for the equations. I'm going to do it for both of them here. So this is an alternative method. So if you don't want to see this, if you think it's going to confuse you, I would say, stop the video. You got enough to get you through here. So I'm going to start with an equation. Absolute value of x minus 4 equals 5. How I did it is I said x minus 4 equals 5, and x minus 4 equals negative 5. That's how I set up the problem. That is a legitimate way, and I hopefully I showed how that worked out logically from working back from a simple example like this, where you'd say, oh, this number, whatever this thing is in here, is a 5 or a negative 5. So I just continue that. Whatever's in here is a 5, so whatever's in here is either a negative 5. That makes sense based on that previous example. But there is another way you could do this, and that other way is you would get this first problem exactly the same, but this second problem you would get negative x plus 4 is 5. And the idea there is, think about if you had a negative 5, and you said that's equal to 5. Well, then what you're saying is the opposite of negative 5 is 5. And so you're taking the opposite of whatever's already in there, and you're setting it equal to this 5. So you're saying in one case, if this was a positive 5, then it's all good to go. 5 equals 5. But in the other case, you would need to do the opposite. And so that's what this idea is here. Now, we're going to get the same answers both ways, whether you do it the way I showed or you do it this way. Whoops, I guess I don't need that. Subtract 4. All right. So negative x equals 1, divided by negative 1, x equals negative 1. You know, and you can plug that in. Negative 1 minus 4 is negative 5. Absolute value, that is 5. So it does work, and 9 minus 4 is 5, and absolute value, that is 5. So, you know, this is an okay. What's nice about this is this alternative method is it allows you to kind of skip some steps if you wanted to, say, solve, say, 4 minus 3 absolute value of x minus 6 equals 1. Okay, you know, what I would do normally is I would subtract 4 and then I'd divide by negative 3. This method allows me to get away from having to do that. I can just say, oh, let's just do 4 minus 3 times x minus 6 equals 1, and then 4 minus 3 times negative x plus 6. So instead of worrying about changing things on the other side of the equation, which would not work in this case until I move things around, I'll just change the things inside the absolute value, and that will give me the right answer. And then you can work both of those problems out, distribute your negative 3, combine like terms. What's that? 22. So subtract 22. Negative 3x equals negative 21, divided by negative 3. X equals 7. Again, distribute. This time, this is going to be a positive 3x minus 18. So combine like terms. 4 and negative 18 give you negative 14. Add 14. I'm getting ahead of myself. 3x equals 15 divided by 3. X could equal 5. And then you can try both of those. 7 minus 6 is 1. Absolute value of 1 is 1. So 4 minus 3 is 1. Absolute value, or sorry, 5 minus 6 is negative 1. Absolute value, that is 1. 1 times negative 3 is negative 3. 4 minus. So both work. So that's kind of a nice thing to find out. But notice I kind of had to check my answers here to do that. But why not do that? Why not use that here? Let's say we had instead 5 minus 1. Oops, I know in a parenthesis. 5. Let's not do 1. 5 minus 2 absolute value of x plus 3 is less than 3. Okay? So we have that. Is this an and or an or? The answer is I don't know yet. Until I get it by itself, I can't tell. So, you know, it might even be one of those special cases. You know, maybe it's no solution. Maybe it's all real numbers. I don't know. The only way to find out is I kind of have to, well, I'm not going to do it that way. I'm going to try to use the method we talked about. So I'm going to, you know, 5 minus 2, parenthesis, x plus 3 is less than 3. And or, I don't know. 5 minus 2, parenthesis, negative x minus 3 is less than 3. So again, you know, instead of changing the stuff on the outside, which means I'd have to move everybody around initially, what I'm going to do is I'm going to change the sign of the things on the inside of the absolute value and then work it out. So 5 minus 2x, distribute to negative 2. Combine like terms. 5 and negative 6 make negative 1. So add 1. Negative 2x is less than 4. Divide by negative 2. X is greater than negative 2. Something, you know, and then same thing, distribute this. Negative 2 and negative x make a positive 2x. Negative 2 makes a positive 6. That's going to give you 11. 5 and 6 make 11. Subtract 11. 2x is less than negative 8. Divide by 2. X is less than negative 4. Now, if I think about what that looks like on the number line, again, remember you got 0 over here. Negative 2, negative 4, greater than negative 2, so that way. Less than negative 4 that way. So I'm thinking this is probably an OR, because it would have to be separate. An OR would do that for you. And means they have to overlap. These don't overlap, so I'm hoping this is an OR, but not 100% certain it's an OR. And so I would probably have to pick some numbers here and test them and see if it worked. And, pick a number, like let's say I put 0 in there. I'm saying, do these numbers actually work? Well, let's see if 0 works. So if I put 0 in there, this would be 3. Absolute value of 3 is 3. So 3 times 2 is 6. So 5 minus 6, is that less than, yeah, that's negative 1. So that does work. And then try negative 4. So let's say negative 5. Negative 5 plus 3 is negative 2. Absolute value is 2 times 2 is 4. 5 minus 4 is 1. Yeah, that works. Okay. So it looks like it's going to work. So this is an OR, but it's questionable, and that's the danger here. And this is why I don't really recommend this method, of doing the problem. But it can work in certain situations, and it may be something you would think about if you want to try this alternative method. But I would really recommend not doing that. It's really easier. In fact, if you look at this, I did a lot of the same kind of work twice. Whereas if I had just subtracted 5 right out of the get-go here, and then divided both sides by negative 2, I would have a much simpler, I guess I divided by a negative, so this would switch, a much simpler problem to work with than both of these problems. By investing a little time in the beginning, you're going to save yourself a lot more time later on. So I really recommend you set it up to 2 problems how we set it up. But at least if you go here and then you set up to 2, you would know, yeah, I'm looking for an OR. So there's going to be solutions here. The question is whether it's going to be all real numbers or specific sets of numbers, and this has specific sets of numbers because this is, there are some numbers that aren't bigger than 1 or equal to 1, that are actually equal to 1. So there's going to be some things that don't work, and that's why we have this gap in the middle here. Okay, anyway, thanks for watching.